Hello everyone, my name is Alessandro Beghini and I'm a structural engineer at Srm. Today I'll talk about the application of robotic technology to the construction of a glass vault. The glass vault is a glass brick structure assembled with cooperating robots without the use of any falsework. It is an exploration on the potentials for robotic construction for complex masonry structures. The project is a collaboration between Srm, Princeton University, and a number of other partners. In order to place the glass vault project in the proper context, we need to start with the Srm Structural Exhibitions. For a number of years, we have had traveling exhibitions showcasing the research work conducted at Srm in the structural group. These exhibitions became also an opportunity to display some of the latest technologies in design and construction as shown in these images. The robotic glass vault represents the latest example of design showcasing futuristic construction technologies, and it was displayed at the Ambika Gallery in London. There is a bit of history behind our research in vaults. We have been collaborating with the Timbre Vault workshop and the University of Alcalá in Madrid for a number of years. Our collaboration resulted in the Timbre Vault showcased at the Madrid exhibit in 2019. Here is a picture of it. Timbre vaults are very efficient shell structures that have the additional benefit of being self-supporting as they're built and can be constructed without formwork. Based on the previous experience with the Timbre Vault, we set some objectives for ourselves to follow in the glass vault design. First, we wanted the construction to be automated, so we thought about using robots. The second objective was to build a vault without formwork, but also without the visual guides that were used by the masons in the Timbre Vault construction. We also wanted to use standard bricks of one size and shape, without custom shapes. Finally, we were looking for a structurally well-behaving shell that would be primarily in compression under gravity load, so we used a form-finding method based on the Airy stress function. In the assembly approach, we were inspired by ancient barrel vault techniques from the Byzantine era. We ended up using a construction approach similar to the one on the right, which relied on inclined courses of bricks layered against a vertical end wall to construct a vault without formwork. Essentially, the form is constructed as a series of arches leaning against each other as you move away from the vertical wall. This approach guarantees stability throughout the construction process at each step of the assembly. The form-finding process utilizes the Airy stress function approach, and it requires the definition of states of self-stress, satisfying certain requirements. Each state of self-stress defines a planar, self-equilibrated system of forces in the shell, which is studied using graphic statics. The images on the left show the form diagram and force diagram used for the glass vault. After the definition of the form and force diagram, the Airy stress function can be calculated and the three-dimensional form of the vault is derived from that function. With the help of the Technical University of Delft Glass and Transparency Research Group, we compared the advantages and disadvantages of mechanical and adhesive connections. Reassembly interlocking glass components would allow the structure to be assembled and disassembled without any joint material. However, to achieve a vault with a complex geometry, several special glass pieces would need to be cast. This was not economically feasible, and it was not in line with the intent of using standardized components. We settled on using a rigid epoxy in combination with acrylic pieces for the larger gaps. After defining the form for the vault, we studied various tessellation patterns for the brick placement. We ultimately selected the herringbone pattern, which allowed the bricks to naturally lock themselves in place and ensure a higher structural stability. To numerically study the equilibrium of the glass vault during all phases of construction, we adopted an iterative procedure based on the limit state analysis and the discrete element method. This analysis allows us to study the stability of the vault at each stage of construction. The image on the left shows the construction sequence of the central arch of the vault, and the image on the right shows a few steps of the sequence analyzed in 3-deck. There is a companion paper here at the conference that goes in greater depth on the analysis discussion. There are a lot of potentials in robotic technology. Automation and placement precisions are the most obvious advantages. However, there are also advantages for construction of spanning structures like an arch. if we adopt a collaborative robotic assembly strategy. If one robot acts as a support while the other robot places a new brick, then the arch can be built without formwork as shown here. We specifically use the robotic setup to identify and visualize the design space that spans between the robots and the logical construction sequence, which ended up as indicated here. First, the robots collaboratively build an arch at the center that serves as a backbone of the vault. Afterwards, each robot continues the assembly individually on each side of the arch, while still serving as a support by counteracting the forces applied to the arch from the opposite side. All of the design and construction aspects of the vault were validated through physical testing, from material connection test, robot reach, path planning, and sequencing. These prototypes started small, as you can see in the images on the left, and increased in size and scope. We eventually built a full-scale prototype, as shown in the images on the right. After successfully building the vault prototypes at Princeton University, we proceeded with the final construction in London. This is a sequence of images of the final installation. One of the most meaningful outcomes of the project was the understanding that new technologies have a way of shaping our thinking about design and construction and bring a new form of architecture. Finally, I'd like to thank all of our collaborators and team members listed here, and thank you very much for your time.